Alright, so let's do a couple more examples for the method of cylindrical shells. Here we got an example where we have y equals the root x going from 0 to 2, and it's being rotated about the x-axis, okay? And it's bounded below by the x-axis. So, as always, the first thing we're going to do is draw our cross-sections. Our axis of rotation is going this way, so we're going to be we're drawing it parallel, right? We're drawing the cross-sections parallel to the axis of rotation. So, now I can actually set up the integral. I'm going to give myself some placeholders and then ask myself, where am I going in a dx or dy? Am I going from cross-section to cross-section? Am I going up, down, or left, right? Well, obviously, I'm going up, down, so I'm traveling in the y direction, so I'm going to have a dy. Then I'm going to ask myself, well, where do I start and where do I stop? Where does my region start and where does it stop? Well, it starts at y equals 0. And it goes all the way up to here. It's bounded above by this little point, but I don't know what the y-coordinate of that point is. What I do know, though, is the fact that it lies on y equals root x, and its x-coordinate is 2. Okay? And that's all I need to figure out is y-coordinate, because if it lies on y equals root x, the x-coordinate is 2, and it's got to be, the y-coordinate has got to be root 2, right? So I'm going from 0 to root 2, okay? Now, what about my circumference? My circumference, the 2 pi is just going to be 2 pi from the 2 pi r. And the r is going to be how far away each cross-section is from the axis of rotation. So each cross-section is going to be, again, y units away, right? Where y is the y-coordinate of each cross-section, because that's just how far away from the x-axis it is. And remember, this is exactly what we expect. We expected this expression to be simple because our axis of rotation is aligned with the x-axis. So what about the height? Or here really it's the length of each cross-section since they're going left, right, not up, down. So, okay, it's still the same idea. We're starting on this curve, we're ending on this curve. So we're bounded left by this curve, bounded right by this curve. This curve is easy to parameterize. It's just x equals 2. It's just constant. This one is a little more tricky. Now, we know how to represent it in terms of x. We know it's y equals root x. But we can't do that, though. We need to parameterize it in terms of y because our integral is in terms of y. And we can't have x's floating around, right? So really, what we need to have is x equals something so that we can say, OK, well, at each y, it's starting at x equals, my cross-sections are starting at x equals something, going to x equals 2. Well, how do we do that? We just square both sides, right? This is a simple example. If you had a more complicated function, all you have to do, again, is to solve for x. Okay? Here, it's a little simple. And we can just say y squared is equal to x. And now we have it in terms of y. Simple enough. I'm starting at y squared, and I'm going to 2. So the distance between these two things is just going to be 2 minus y squared, because it's bounded left by y squared and bounded right by 2. And that's it. And you can just do the integral again by distribution. Very simple. Let's do another example that's a little more subtle. So as always, we're going to draw our cross-sections. My axis of rotation is going like this. My functions, by the way, are minus x times x minus 2 and y equals 0. So this is my region. So my axis of rotation is at x equals 3. So my cross-sections are going to be like this, parallel to my axis of rotation. So now I'm going to actually go ahead and set up the integral, give myself some placeholders. Actually, I'm going to make them a little bigger. So now I'm going to ask myself, am I going dx or dy? Am I traveling in the x direction from cross-section to cross-section, or y? Well, I'm going in the x direction, so I'm going to have a dx. Where do I start and where do I stop? Well, I start at x equals 0, and I stop at x equals 2. And you can note those are the two zeros of the function, because that's where these two functions, my boundaries, intersect each other, so 0 to 2. Now I'm going to ask myself, well, what's my circumference? The 2 pi is just going to be 2 pi. Now the r is going to be, again, the idea is the same, the distance between each cross-section and the axis of rotation. However, now the axis of rotation isn't aligned with the x or the y axis. So what we have to figure out is how far away from 3 each cross-section is. Not 0 or, x equals 0 or y equals 0. But now we have to figure out how far away from 3 each x-coordinate of each cross-section is. That's very simple. We just do 3 minus x, right? Where x is the x-coordinate of each cross-section. So if the cross-section is at x equals 1, it's 2 units away from 3. If it's at x equals 0, it's just 3 units, right? So it's 3 minus x. Again, because we're trying to find how far away from 3 each x-coordinate is. Now, we got to do our height. Our height is simple. It's just our region is bounded above by y equals minus x times x minus 2, and below by y equals 0. So we don't even have to write it. But if we had a lower bound, we would say this guy minus our lower bound. But since our lower bound is 0, it's just minus x times x minus 2. Okay? And there you have it. It's, again, very simple. This is a fairly complicated example. But again, if you just follow sort of the procedure and think about each detail carefully, there's nothing hard about it. And there you have it.